Recording in progress.
Okay, yeah. So this was problem A. So I'll discuss the statement at first. So problem A. So in this problem, we're given an array and we need to break the array into k continuous segments. So yeah, we're given k, right? Yeah. So we need to break the array into k continuous segments. So for example, if k was free, then we could have done this. So k continuous segment means that we'll divide the array in two places like this. So the score of a subarray if LR is denoted by, so let's say a subarray from L to R. So the score of this is denoted by the absolute value of all the adjacent differences, the sum of the absolute value of all the adjacent differences. So we'll take AL minus AL plus 1, AL plus 1 minus AL plus 2, and we'll do this up to A of R minus 1 minus A of R. So the score of a subarray from L to R is this. This is the score. So our goal is to break the array into k continuous segments so that the sum of all the scores is minimized. So we'll calculate a score for this subarray, this array, this subarray, and this subarray. So our goal is to divide the array into such subarrays that the sum of all their scores are minimized. So let's take a look what happens when we divide a subarray. So let's say we had a subarray from 1 to 3. So the score for this subarray will be A1 minus A2 plus A2 minus A3. So 1, 2, 3. This was the subarray. So if we make a division here in between 2 and 3, then this difference 2 to 3 will not get this anymore. So the difference from A2, the difference between A2 and A3, this will not be present anymore. But A1 minus A2 will be present. So if it was a bigger example, if the subarray was from 1 to 4, then the score would be initially the sum of these three. But if we make a division between 2 and 3, then again this sum would disappear. So this difference would disappear. So this is what we're doing when we make a division at some place. The difference between the two elements before it and after it will not be present in our final score. So we can follow this greedy strategy. At first, we'll take all the adjacent differences. And from those differences, as we need to make k groups, so we need to make k minus 1 divisions. So we'll just remove the k minus 1 largest values from these differences. So we'll take n minus k minus 1 smallest differences and sum them up. So that is going to be our answer. So did everyone understand this?
Bro, can you repeat the n minus, like how did you come up with n minus k minus 1 part?
Okay, so this will be n minus 1 minus k minus 1, my bad. So there are n minus 1 differences at first, and we're getting rid of the highest k minus 1 differences. So we'll have n minus 1 minus k minus 1 differences left. So we'll take the smallest such amount of differences.
So we should just sort them and find out the k minus 1 smallest values.
No, we'll get rid of the k minus 1 largest values.
Okay,
because we have to minimize the final score.
So, okay, so the final answer would be sum of smallest k minus 1, no?
No, the sum of smallest n
K
minus
minus
1 minus k minus 1.
sorry, n minus 1 k minus 1.
Yeah.
Bro,
So
can
we
you
have
do
to
one
find.
small dry run, no, for this?
Yeah, sure.
Sir,
Can you tell me sample?
I could not get from there where which we will divide the array at some indexes and the differences will disappear. From there, I could not get.
Okay, did you understand that if we divide that difference will disappear? Did you understand that part?
Yeah, I got that.
Yeah, okay. So we can divide at any such places, but we should divide in some place where the difference is maximized. So if we get rid of that, the leftover score will be minimized, right?
Uh, Means we will divide at those point which gives maximum difference.
Yeah. If we get rid of those, the leftover score will be minimized. So that is why we're taking such highest differences.
Sir, can you give some just example what you are saying?
Yeah, okay, sure. So let me dry run a test case. So I'll take one of the samples. So let's take 1, 9, 12, 4, 7, 2. So we have 1, 9, 12, 4, 7, 2. So what the value of k is 3 here. So let's write down the differences first. So the differences are 8, 3, 8, 3, 5. So if we sort them, the differences are 3, 3, 5, 8, 8. And as the value of k is 3, we need to remove the highest two differences. So we remove 8 and 8. So our leftover score will be 5 plus 3 plus 3, that is 11. As you can see, the answer is 11. So
Okay,
yeah,
okay.
any doubts?
No, it's there.
Okay, so did everyone else understand? So
Yes,
I'll
bro.
just quickly show my code. Okay, let me just quickly show my code to you guys. Yeah, so here we're taking n and k in input, and we'll also take the array in input. Then I made a vector, and in that vector, I'll insert all the adjacent differences. So I'll run a loop up to n minus 1, and I'll just insert absolute value of array I minus array I plus 1. Afterwards, I'm sorting the values from larger to smaller. So the largest values will be at first. So then I'll just take the sum from the k minus 1th index to n minus 2th index. So I'm getting rid of the first k minus 1 values. So I'll add the smaller values here, and then I'll print out them. Yeah, so any doubts?
No, sir.
Okay, so let's move on to the next problem now. Okay, so yeah. So in this problem, we're also given an array, and we can divide the array into some number of segments. And for this problem, the core of a segment, FLR, is the bitwise AND value of all the elements. So okay, problem B. So we have this array, and the value of a segment is the bitwise AND of all its elements. So we can divide the array into some number of continuous segments. And the score of the array will be the sum of all the segments. So the sum of all the AND values of all the segments. And our goal is to minimize the total score So we have to answer the minimum number of segments, or sorry, we have to find out the maximum number of segments that we need to divide the array into to get the smallest score of the array, or the smallest sum of string. So this value FLR, or a score of a subarray, the n values of all its elements, they're calling it the string. So the score of the total array is the sum of all these strings. So our goal is to find the maximum number of segments that we can divide the array into, and also get the minimum amount of score. So at first, one property of bitwise AND is that, let's say we have 4 elements into a group. If we add another element into this group, then the bitwise AND value of all these 5 elements can only become smaller. So let's say the AND value of this group was A, and the AND value of the total group is B. So B will always be less than or equal to A. B can never be greater than A, because that is the property of bitwise AND. In bitwise AND, while we're taking AND between two values, if both the bits contain 1, then we'll take a 1. But if one contains a 1 and another contains a 0, then we'll take 0. So some 1 bit can stay 1, some 0 bit can stay 0, and 1 bit will can also become 0, but 0 bits can never become 1. So the value will never increase. So the value of B here will always be smaller or equal to A. So that means if we add a new element, that will always give us a smaller or equal value. So by that theory, getting the smallest getting the smallest score, we'll get the smallest score when we take the whole element into one segment. So we're doing this, we're taking the taking the whole array into one segment, and so we're taking the bitwise AND between all the elements. So this is our first approach. We're going to calculate the minimum score of the array by taking the bitwise AND of all the elements. So did everyone understand up to here? Yes. Okay, so if anyone has any doubts, you can feel free to speak up. Okay, so now we have to find the maximum number of groups we can divide the array into, and while maintaining that minimum score.
But yeah, sorry to interrupt. Like
Right.
if we add all the elements, the sum will be less than or equal to the maximum element of array.
Yes.
Okay.
Okay. So there can be two cases. Case 1, when the score that we calculated by taking the bitwise AND of all the elements, so the score is 0, and the second case can be the score can be non-zero. So this is not equal to 0. So let's take a look at the second case first, because it's much easier. So let's say the bitwise AND of the total array is 28, for example. So 28 is 16, 8, 4. So this is the bitwise representation of 28. So we'll get 28 by taking the bitwise AND of the whole array. But let's say we want to divide the array in some place here. So let's call this A. So let's call the bitwise AND of these 3 elements A. So A is greater than or equal to 28. Does that make sense? because as I said, if we add more elements, the bitwise end will only get equal or smaller. So the bitwise end of these three elements has to be greater than or equal to 28. Yes. So if this subarray has a sum of greater than or equal to 28, and this subarray will have some value. So wait, let me think for once. Yeah, as this subarray, so we're dividing the array into these two parts. So if this subarray has a value greater than or equal to 28, this subarray will also have a value greater than or equal to 28, because you can think of it like this, that we're adding elements before this subarray. So if we add elements before this subarray, they'll only get smaller or equal. So as the whole subarray has a bitwise end value of 28, then this subarray will also have a value at least 28. So if we take the sum of these two values, so 28 plus 28, this will obviously be greater than 28. So it turns out that if the score is non-zero, then we cannot divide the array into more than one part. The array will have to remain in one part. So then for this case, when the score is not zero, then the answer for it will be 1.
Sir, can you just repeat how did you reach that answer will be 1? The subarray will be greater than equal to 28. I got that.
Yeah. So if we just divide it in one place, both the subarrays will have a value greater than or equal to 28.
Yeah.
So the sum will be greater than 28, then we cannot get the minimum sum 28.
Okay. The and will increase. Okay.
Yeah. So that is why we need to take the whole array as one segment. So the answer for it will always be 1 if the score is non-zero. So anyone have any doubts in this part when the score is non-zero?
No, sir.
Okay, great. So now the case for bitwise end equal to 0. So for this case, we know that the bitwise end is 0 of the whole array. So what we can do is we can take some segments where each segment has bitwise end equal to 0. Then all their sums will also be 0. So we can do that. So we'll do this algorithm. We'll go from left to right greedily. Let's say we're going from left to right, and when we're at the first index where the bitwise end of this segment is 0, we'll call this is one of our sections. Then we'll start another segment from this index, and we'll check the first index where the bitwise end again becomes 0. We'll mark it as another segment, and we'll move on. So what we're doing is we're greedily going from left to right, and we're taking out segments where the bitwise end of that segment is 0. Make sense?
Sir, but since
Yeah.
the and of entire array is 0, so if we divide it, then the and will increase. But
We're not dividing in such a way that the score becomes more than 0. We're only dividing the array when the score becomes 0. So the bitwise end of these three elements becomes 0. Only then we're dividing this part. Okay.
Since the score is 0, so at any time we have and as greater than 0. So how we are going to get the segments that have and 0? Means agar एंड कुछ पार्ट के लिए जीरो से पहले इंक्रीज करेगा, फिर वो अचानक डिक्रीज तो होगा ही नहीं। मतलब अगर सेगमेंट और इंक्रीज करेंगे तो वो तो बढ़ता ही जाएगा ना। तो मतलब ये लॉजिक नहीं समझ आ रहा कि सेगमेंट में जीरो कैसे आएगा।
Bitwise end cannot decrease. Are you saying that the end value will increase? It
यस।
cannot increase. Yeah, bitwise end doesn't have that property. Bitwise end will always decrease.
ओके
Yeah.
ओके
Yeah, so it
Okay.
will keep decreasing. When we get the bitwise end value 0, then we'll separate this segment and start a new segment.
ओके ओके
Yeah, so we'll keep doing this, but there can be one case when, so let's say one case is when we can divide the array into 3 segments where all these segments have a bitwise end of 0. But it can be a case like this, that we have end equal to 0 for this segment. We also have end equal to 0 for this segment, but this segment does not have end equal to 0. So we cannot make this a new segment. We can just merge this with the previous segment and call this to one segment. The bitwise end value of these two segments will remain 0. So this is just one corner case that you have to be careful about. So any doubts?
Sir, I'm still getting confused in this part. How we are
Which part?
this part we are counting the segment and we are getting the segments and as 0.
Yeah, because bitwise end always will remain the same or decrease as we add new elements, right?
Either will be same or decrease. Fine.
Yeah, it will be same or decrease. So eventually it will decrease. So eventually it might become 0, right? So let's say after coming to this segment, the bitwise end of this part becomes 0. Okay.
Okay.
So we'll mark this as a separate segment and we will start a new segment from here. So was this your doubt?
So if we'll mark this, then the can we say that the end of further segments will also be 0 because it is not going to increase anyways.
It might not become 0. As I said, there can be one case that we might be left with some segment that is not 0, but we can merge this segment with the previous segment to get a total bitwise end value of 0. So
Okay,
we'll not count the new segment as a segment in our answer.
Yeah, okay, sir.
Okay, so yeah, this is the tricky part. The bit where we that we're left with, that is not 0, but you guys understood how we're handling that, right?
Yes, sir.
Okay, yeah. So let me just quickly show my code. Okay, yeah. So we're taking the array in input here, and I have a I have a variable a that contains 35 ones. So 2 to the power 35 minus 1. That means we have 35 ones in its bitwise representation, and the b variable also contains those 35 ones. So then we can add all the values of the array with b to get the bitwise end value of the whole array. So if b is non-zero, then we need to print out 1. Otherwise, we'll take we will greedily take segments from left to right when the segments have a bitwise end of 0. So we're running a loop here. We're taking bitwise end of array I in the variable a. If a is 0, then our answer increases and we reset a with 35 ones. And then we keep doing this. So as long as we get new segments with bitwise end of 0, we'll keep incrementing the answer, and finally we'll just print out the answer. So
Sir,
any doubts?
Yes, sir. Why did
Yeah,
you
yeah.
take A like this, 1NL shift 35 only? Means, is there
So
any specific reason why
yeah,
did you 35?
yeah. Because let's say our numbers can have at most 8 bits. Okay, so the numbers that we are given in the array, they will be something like this. And as we have to take the bitwise AND of all the elements, we need to take A at first like this, so it does not mess with the end value of the given array. It is similar to that if we're taking the multiplication of an array, we take the A equal to
Is
we
it
take A
one?
equal to 1 first. Yeah, this is similar.
Okay, okay. Can't we just initialize with just a single one? But
No, that will not work because the bitwise and because the bitwise representation of 1 is this.
okay, it will affect further bits. Okay.
Yeah. Okay. So any confusions with the implementation?
Hello, sir. I have one more idea. Can you say whether it's right or
Yeah.
not?
Yeah.
So, like, what I'm doing is I'm basically finding the total and of the whole segment.
Okay.
So we will get the minimum and value.
Yes.
So, like after that, I will iterate through the array again to get like. So whenever the segment which reaches the minimum part, I will choose that as one of the groups, and then again goes through the array and I will choose the groups like that. Is it right?
That will not work for the case when the bitwise and is non-zero. As I gave an example of the 28 case, there can be two subarrays that have bitwise and value of 28. So then you'll get the sum of 56. We cannot divide the whole array into two such segments.
Okay.
So that will work for this case, but it won't work here.
So it won't work for what? It won't work for.
When the bitwise and value is non-zero.
Okay.
Okay, so let's move on to problem C.
What is this
Yeah.
FRN in your code?
Oh, so okay, let me just open it back up. So yeah, this one.
Yeah.
So this is just a for loop from 0 to n minus 1. So
Okay.
yeah, that is the same as this.
Okay.
Okay, yeah. So now we have problem C. Okay. In this problem, we are given an array. So problem C, we're given an array and we can do this operation as many times as we want. So it shows your solution for which problem? Let me check. Problem C. Okay, so I guess I was wrong somewhere. Okay, so I'll explain as much. So I'll explain the basic idea. I might have gotten some basic implementation wrong or something. So yeah, I'll just explain the idea. So we're given an array and we can do this operation as many times as we want. We can take a suffix of the current array. So we'll take the bitwise XOR of all these elements and we'll get a new element and we'll append that new element at the end. So this is the first operation. Then again we can take another segment We can take the bitwise XOR of all these elements, and we can take that element, we can take the element that we got and append it to the end of the string. So the question asks us to find the maximum such element that we can achieve by doing this operation as many times as we want. So we can do that operation of taking the XOR value of a prefix and appending that to the end of the array, and we need to return the maximum element that we can achieve by doing this operation as many times as we want. So let's take a look at that operation again. Let's say at first we take this range. So if we XOR these elements, so we'll get a new element which will be the XOR value of this segment. So we can say that we just copied this segment and pasted it here. So when we take another prefix, then this prefix will be included twice. So this will not be counted. So then we'll get the XOR value of only this prefix. So this is the main idea of the problem. What we're essentially doing is we're taking the XOR value of some subarray of the given array, not just a prefix. So we can take the XOR value of some subarray of the whole array. So the problem now is to find out the maximum XOR value of some subarray. So let's say this subarray gives us the maximum XOR value. So what we'll do is we'll pick this prefix at this suffix at first. Okay, so pardon me if I was saying prefix previously, I meant suffix. So at first we'll take this suffix, so we'll paste it here, and then we'll take this suffix. So this part will not be counted because it is included twice. So if some value is included in the XOR and even times, that gets doesn't get counted. So we'll get the XOR value of this subarray. So now we'll get the maximum XOR value. So our job is to find the maximum subarray XOR of the given array. Because let's say some element is this. If we XOR this element with itself, then 1 1 will get 0, get the value 0, and 0 0 will also get the value 0. So if we XOR these two elements, we'll get 0. So that will not be counted. So yeah, is it clear now? Okay, how is XOR cancelled? So I'll explain it one more time. Let's say we have the variable a, and the bitwise representation of this is something like this. So if we do a XOR a, then we're taking XOR of this. So we're doing XOR here. So 1 XOR 1 is 0, 1 XOR 1 is 0, 1 XOR 1 is 0, 0 XOR 0 is also 0, 1 XOR 1 is 0. So we're actually getting the value 0 here. And if 0 is XORed with some other element, let's say x, we get x. So that is why when we're taking two of the same subarrays here, they are getting cancelled and they are getting the value 0. And then we can XOR 0 with this subarray and get the value of this subarray. Yeah. So by max XOR of a subarray, I just mean any subarrays from the given array. So the subarrays of the given array are like this. So all these subarrays. So we just need to find the maximum XOR of some such subarray. So is the observation clear up to this part? Any doubts? So yeah, but how can we know? Yeah, so I'll discuss that. We need max XOR of 2 subarrays. What do you mean by 2 subarrays?
Like you took first time you took one subarray, right, from last till index, and then again you took a bigger subarray, and then you said that the smaller part was cancelled. So basically, we were taking XOR of two subarrays then, right?
Yeah, I understand your question, but the 2 subarrays that I took are just to what can we say? Just to use the operations that was described in the statement. So I'll take this part, and again I'll take this one. So the actual value that we get is from this subarray. So if this gives me the maximum value, this subarray gives me the maximum value, then I'll do this operation. But this operation is not needed for us. We just have to find the maximum value. So we just need to find the XOR value of this subarray. So does this make sense now? I think, yeah. The person who was having the doubt, is it clear now? Or should I explain it one more time?
I didn't get why it is max subarray XOR.
Sorry, can you repeat it?
Like how can you conclude that we just need the maximum subarray of zone, like maximum subarray zone?
How can we figure out? Or I'm having trouble hearing you.
I got your intuition that the smaller part is getting cancelled, but
Yeah.
how does it conclude that we would be finding maximum subarray zone?
At first we need to find the maximum score of the array, right? The maximum element that we can make from the array, right? So we just have to find a way to maximize the element that we make. And if there is some subarray, let's say this, with the maximum XOR value, then we can just do two operations. We'll do this one and this one. Then that will give us the XOR value of this subarray. So this is how we're getting the maximum XOR value, right? So I think this is the intuition behind taking the subarray with the maximum XOR value. So yeah. So now let's move on to how we can find the subarray with the maximum XOR value. So the key was the constraints. The maximum value that we can get is 2 to the power 8. So 2 to the power 8 is equal to 256. So we can get 256 values in input, and 2 to the power 8 is 8 bits. And if we XOR some values which have 8 bits, then the values that we get will also have at most 8 bits. So the XOR values will be contained inside these values. So the maximum XOR value can be at most 255. So we can try all these 255 possibilities. So what we're going to do is we're going to run a loop from 255 to 0. And for all these cases, we're going to try to figure out if 255 can be made using some subarray. So if we can we find the element I, that is from 255 to 0, in some subarray? And how can we find if some value is present in some subarray or not? So let's say this is the given array, and if we take the prefix XOR of this array, so let's say this is the prefix XOR, so this is from 0. So yeah, so let's say we have B here, and we want to make the value I. So we have to have some prefix here. Okay, I'll explain it like this. Let's say we have two prefixes with B and C. So the value of this prefix of this subarray is equal to B XOR C. Does everyone understand this? Because the prefix XOR up to here is equal to C and the prefix XOR up to here is equal to B. So if we take the XOR value of these two subarrays, then the prefix XOR part here, this will get cancelled and we'll get the prefix XOR value of this part. So the prefix XOR of this part is equal to B XOR C. Sorry, the subarray XOR here is equal to B XOR C. So does everyone understand this?
Yes, sir.
Okay, so this is the subarray XOR. So if we know the subarray XOR, we know the subarray XOR here is I, and we know the current prefix. So we can iterate on the total array, and then we'll know the current prefix XOR value, that is B. So if we take, if we XOR B in both these parts, then we'll get C equal to sub XOR B. So if we know the value of sub XOR B, then we know what value of a prefix XOR we need to have previous to the current element. So if there was some prefix here with the value sub XOR B, then the subarray XOR here would be equal to this value. So if there was some prefix here equal to this value, then we know that we can make the value I. Does this make sense? So any doubts? I think there should be doubts. The explanation wasn't very good. If you guys want, I'll explain it one more time. Yeah, okay. So let's say this was the given array and we took prefix XOR in this array. So this is the prefix XOR. Yeah, this is the prefix XOR. So let's say we have two prefix XORs here, B and C. So B covers XOR value of these elements and C covers XOR value of these elements. So if we take B XOR C, what are we going to get? We took the XOR value of this part twice, so this part will get cancelled. So we'll get the prefix, we'll get the subarray XOR value of this part. So is this understandable? Okay, yeah. So now we can take XOR B in both left hand side and right hand side. Then B will get cancelled from the left hand side. So C is equal to so we should take C in both left hand side and right hand side. So we had B here. If we take C in both left hand and right hand side, then we'll get B equal to sub XOR C. So if we know the subarray XOR value and we know the current prefix value, then we know what value we need to have in some prefix. So what the value of B needs to be to get a subarray XOR value of sub. Does this make sense now? So yeah, can anyone respond if this is understandable or not now?
Sir, repeat the last statement. This B XOR
Okay.
C means if we have subarray sub and then C, then we can determine the.
Yes. if we know the subarray XOR value that we need to make, and if we know the current prefix XOR value, then we can determine the prefix XOR value that we need to have previous to the current index to get this to get the subarray XOR equal to sub.
Okay.
So yeah, we are not maximizing it here. We're just running a loop from 255 to 0. So if we get, so we're running a loop from the highest value to the lowest value, and if we're checking if there is a subarray of this value. Okay. So Harsh, is it clear now?
Why some down? Like why we can only form the subarrays? Will it not be possible to form any other subsequence?
I think it is not possible because you're always taking a suffix of the given elements, right? So if you take a suffix here, we'll get some value, and then we can take another suffix and we'll get some other value. So it will be always continuous, right? It should be always continuous, because then let's say we again take this segment, then this part. Okay, wait. So let's simulate this. Let's say we took this part, then we took this part. So we have the value here. Then
But when we took the new part, it will also form a new element. Then we have also to consider this element in the new suffix we are forming. Like one
sorry.
element would be added. Like first we consider the last part, then we add this to the array, and then after adding we will take another suffix. But in this case, I am only performing operation on the original array. I'm not modifying it.
I'm actually not clear what you are trying to say. Can you repeat it one more time?
Like in the question it is given, we have to perform some operation and then add it to the array.
Yeah.
But in the given example, what we are doing is that we are not changing the current array. We are performing operation on the current array only. We are not adding it.
We're actually adding it. So at first, let's say we took this suffix. So we're adding the value of this. So adding the value of 1 to the subarray, 1 to the array. So when we take this suffix, that is when this part is being cancelled, because we have this and we have this. Both of these are the same.
Okay. Got it.
Yeah. Okay. Yeah. So yeah, and did everyone understand this part? If we know the current prefix, XOR value, and if we know the subarray value that we need to make, then we can figure out the prefix XOR value that we need to have previous to this index. So we need to have some prefix value here to make this subarray value. So if this prefix XOR value exists before the current index, then we can say that we can make I, otherwise we cannot make I. So that is how, so we're going to keep track of all the prefix XOR that we have previous to the current index. So if this is the current index, so we're going to keep track of all these prefix XOR values, let's say in an array or in a map, and then we can figure out B, and we'll see if we have B inside our map or not. In that way, you can figure out if we can make I. So my code got wrong answer on system tests. So I'm not going to show you guys my code because there are some bugs in it, obviously. So just try it out. I think this is the correct approach, or there might be something wrong with my approach as well. I'm not sure. Okay, so any more questions about problem C? Okay, yeah, so let's move to problem D now. So in this problem, let me clear everything here. So problem D, we're given a binary string. So we're given binary string and we're given some ranges. So let's say we're given 2 to 4. I'll mark the indices here. 1, 2. So we have 2 to 4, 6 to 8, 5 to 10, 1 to 3. Let's say we have these 3 ranges and we'll be given some queries. In each query, okay, let's make, I think it was T of S, yeah. So we have another definition, that is T of S. T of S is, we're going to take this subarray 2 to 4 from the original string. So at first we take 2 to 4. So 0, 1, 1. Then we'll take 6 to 8. We'll concatenate all of this. So we take 6 to 8, 1, 0, 1. Then we'll take 5 to 10. So 5 to 10. 0, 1, 0, 1, 1, 1. Then 1, 2, 3, 1, 0, 1. So what we're doing is we're taking all these substrings from the given string in this order that is given in the input, and we're concatenating all these substrings to get a new string. So this is T of S. So we were given one operation where we can take 2 indices and swap the characters of these 2 indices. So if we pick these 2 indices, then we can swap these characters. That is what we can do. So we have Q queries. In the queries, we'll be given an index. So let's say this is the index. We need to flip the value of this index. So if we flip this, 1 will become 0. And if let's say this is the given index, then 0 will become 1. So we're not actually performing the updates on T of S, we're performing the updates on the given string, which is S. So if this was the given index, 0 will become 1. If this was the given index, then 1 will become 0. So after each of the queries, so after we're done updating, after we changed 0 to 1 or 1 to 0, then we make T of S for each of the given queries, and we need to find out the minimum number of operations that we need to make T of S lexicographically as large as possible. So yeah, this was a pain of a statement to understand, but I hope you guys understood. Is there anyone who didn't understand what the statement was saying? Okay, so let's move on to the solution now. Okay, at first let's figure out the solution if there were no updates. So we just have some ranges and we can perform some operations on it, some swapping operations on it. And we need to figure out the minimum number of swapping operations. So swapping operations in the given string. So the swapping operations on the given strings to make T of S as large as possible. So what does lexicographically largest means? We'll have as many ones in front as we can, and we'll have as many zeros at the last as we can. So we'll try to take all the ones at the front and try to take all the zeros at the back. So what we're doing is, at first we'll take this segment, then we'll take this segment, then we'll take this segment, then we'll take this segment. So we're doing this in order. So we're taking the segments from 2 to 4 at first. So if we're taking the segment 2 to 4 at first, then we want to make the elements from 2 to 4 once. If we want to make T of S lexicographically largest, so the substring from 2 to 4, we want to make all these elements once. So as we need to make them once at first, I'll give them a priority. The priority of 2 is 1, 3 is 2, and 4 is 3. Then we need to take the substring 6 to 8. So 6 to 8, I'll give them priority 4, 5, 6. Then we need to take the substring from 5 to 10. So this substring, so this will get a priority of 7. This indices already has a priority, so they will remain the same. Then we need to take the substring from 1 to 3. So we'll assign priority here. So this is how we're going to assign priorities from top to bottom. We're just assigning priorities to all these indices. So now let's take a look at what happens. We have 1, 2, 3, 4, 5, 6, 7 ones here, right? We have 7 ones here, and we want to assign ones to the first 7 indices with priorities from 1 to 7. Because if we do that, then we make T of S as lexicographically large as possible. So we want to add ones here. We want to have all ones in these 7 indices which have the smallest priority, or you can say largest priority. It doesn't matter. The priority means that we have to assign ones to them first. So we'll take a look at how many zeros we have in these indices from priority 1 to 7. So yeah, so we'll take a look at how many ones we have. So we have 1, 2, 3, 4 ones here, and we have a total of 7 ones. 7 ones. We have a total of 7 ones, and we have 4 ones in these 7 priorities. So we need 3 more ones here. So if we take these ones, we can assign to these 3 indices, and that will give us the lexicographically largest value. So the calculation is the number of ones minus the number of, okay, this is the number of ones. This is the total number of ones minus the number of ones in the first, let's say, let's say there are P ones, for example. So number of ones in the first P priorities. Because there are P ones, we can have at most P ones. So if we take the number of ones from the first P priorities, so if we subtract that from the number of ones, then we'll get the number of zeros, and we need to assign zeros to those places. So this will be our answer. This is the number of moves that we need to make to get the lexicographically largest value. So I'll repeat it one more time. Let's say we have P ones, so we can assign ones to P indices, but ideally we want to assign P's to the indices which have the smallest priority. So if we find out the number of ones in the first p priorities and subtract that from the total number of ones, then we will know that the number of zeros that we have among those first p priorities, and we can fill them with the other ones that we have. So these are the 3 ones that we have. So we can just swap these ones here with these zeros to get the largest, lexicographically largest value. So does this make sense now up to here? Yes, sir. Okay. So now what do we do when we have queries? So in one query, some 0 will change to 1 or some 1 will change to 0. So, and we know which index it will change from. So let's say we maintain an array. Let's say we maintain something. So let's say these are ordered by the priorities. So these are the priorities. And we know for each of these indices, if it is a 1 or it is a 0. So if there are currently 5 ones, so from 1 to 5, we can take a look at how many ones we have and subtract that from the total count of ones. So we'll get the answer 2 here. So we need to maintain some structure which will allow us to update the individual indices, and we can get a range from for some index, for some range. So we can use a binary index tree or a segment tree for this. So we'll keep a segment tree or binary index tree on the priorities, and we can update those values using from zeros to ones or ones to zeros, and we can query in some range to find the count of ones in that range. So yeah, does everyone understand how we're going to get the final answer if we have updates?
Yes.
Yeah. So anyone has any doubts?
How we are maintaining the priority?
How we're maintaining what?
Priority.
Priority. So we'll just calculating the priorities at first. So I'll erase them. So the priorities will never change because the order of these ranges are fixed. The order of these ranges are given to us at the very beginning. So at first, before processing all the queries, we'll just process all these ranges and we'll assign priorities. Then it will become fixed. And how can we assign these priorities? Let's say we have a set of all these indices from 1 to 10. Now, if we're given this range 2 to 4, we'll check the elements from 2 to 4 in that set and we'll assign them priorities from 1 to 3. Then again, for this 6 to 8 range, we'll check which values we have in the set and we'll assign them priorities and we remove them from the set. Now, when we get 5 to 10, then the set will contain 5, 9, and 10. Then we assign them priorities in increasing order. Yeah. So, yeah.
Sir, I guess we can do it without segment trees also. Like we can do it. Like we can keep a pointer at the Piet index, and if we are changing the Piet index from 1 to 0, we will we know that first P, we know at the beginning we know that in the first P, like we have P1s, and in first P elements how many ones are there. So if the P, so whenever a 1 is changed to 0, P will be decreased by 1, and whenever 0 will be changed to 1, P will be increased by 1. So if that one is one that is being changed from 0 to 1 is at Pth index, so like our answer is P minus x, then x should be x should also be decreased by 1. That and if if we are increasing the We are converting 0 to 1, and if that 0 to 1 is within in the range 0 to p, our x should also increase by 1, and in other cases
Yeah,
like am I able to
yeah,
convey?
I understand. Yeah, it should also work. Yeah, but thinking about this seemed easier to me. So yeah, this is how I did it.
Actually,
Let me.
I tried using it with segment tree, but I got wrong. I got wrong answer, and there was some implementation fault, I guess.
Yeah, so yeah, one edge case that I found was we cannot assign one to indices if we don't have. Okay, so I'll give an example here. Let's say this was the given array, and the ranges covers these elements. So the ranges will not cover these two elements. So assigning ones to these indices will not help us in any way. So we need to be careful about these indices so that we don't get an overcount. So I'll show you guys my implementation really quick. So we have n and m. I'm taking the string in input, and I'll use one base indexing here. So that is why I'm just adding a hash in the beginning of the string. We also have an array of pairs. In this will I'll take input all the ranges. I also have an array of the priorities, and I have the set where I inserted all the elements from 1 to n. So in this loop, so we're taking m ranges in input. So these are the ranges, and in this loop, I'm assigning priorities. So for each iteration, I'm calculating the lower bound of array I dot first. If it is equal to st dot end of if the value of this is greater than array I dot second, then we can break. Otherwise, I'm taking the value in the variable val. I'm erasing the val element from the set, and I'm assigning the priority of val to c. So c is initialized with 1 at first, and I'm incrementing c at each step. And I also have d here. D will denote the number of indices that are covered by those ranges. So for the last example here, these two indices were not covered. So the D variable will contain value 5 here because we have 3 and 2. So here we have a total of 5 elements covered by the given ranges. We'll use this later. So I'm assigning priorities to all the elements that are not covered by those ranges. I'm taking another array, and I'm adding a pair to this array where the first element of the pair is the priority and the second element is the element which has that priority. So if I sort all those values, I'll get priorities from smallest to largest. So I guess, yeah, I did not use this. I used this for another approach, but this is not needed now. So I'm counting the number of ones here, and I'm updating the priorities. If the current index contains 1, then I'm updating that priority with a 1. So I'm using a binary index tree here, the BIT here. So I'm updating that priority with the value 1. So I'm adding 1 to that priority. So now this is for all our queries. We take the index in input. If the index contains 1, it will become 0 now. So the number of ones decreases. We update the current priority with -1 because this will not contain a 1 anymore. So if it contained 1 previously, so if I add -1 to it, it will now contain 0. And I'm taking answer here by once minus query in once. So yeah, So what I'm doing here is, so this is the array, this, yeah, okay, yeah, so this does not matter, we only need the number of ones. So the one variable here contains the number of ones, so our answer is ones minus the number of ones in the priority of 1. So if the priority of 1 is 4, then we just need to find the number of ones in this range. So we actually need to do ones minus query up to ones, but I'm adding d here because, as I said, if the number of ones is more than 5 here, so then we are adding ones to these indices, but that doesn't help us in any way. So I'm just minimizing that with d. So min d ones minus query min d ones. And similarly, if the current index contained a 0, I'll increase the number of ones. So the number of ones will increase. I'll update the priority of the current index with a 1. And I'm taking min d ones minus query min d ones. And I'm changing the current character to a 1. Yeah, so any doubts? So yeah, I guess no one has any doubts. Yeah, so this was the session for today. Thank you guys for attending.